Hi, this is Mrs. Villette. In this video, we'll go over section 5.1, which covers rational exponents. In order to understand what a rational exponent is, we need to recall what a rational number is. So a rational number is just a number that can be expressed as the ratio of two integers. So for example, 2/3, 4/5. Rational exponent expressions are of the form a to the m over n. So what this means is we have some base raised to a fractional power. So an example of a rational exponent could be 2 to the 2/3. This is not 2 and 2/3, this is 2 raised to the power 2/3. We'll start off with what it means to have a rational exponent of the form 1 over n. A rational exponent of the form 1 over n is just equivalent to an nth root. So for example, if I had 9 to the 1/2 power, that would be equivalent to the square root of 9, which would just be 3. So let's do a little bit of practice with rewriting things from radical form to rational exponent form. So radical form means you're going to have a radical symbol, whereas rational exponent form means you're going to have a base raised to an exponent. The thing that I remember with our rational exponents is the denominator always becomes the index of the root. So in this example, we have rational exponent form. We're going to rewrite it as a root of x with an index of 4. So x to the 1/4 is simply the 4th root of x. Now on these, we don't need to simplify, we're just translating. -8 to the 1/3 power. The denominator is 3. That is going to become the index of my root. So it is going to be a cube root of -8. Going the opposite direction, the same thing applies, just in the reverse order. So the index of the root becomes the denominator of the exponent. So this is x, y, z, all raised to the 1/5 power. And the next one is 49x to the 8th raised to the 1/2 power. We need to remember that with square roots, the index isn't usually written, but it is a 2. One important reason to understand why this rule is important is when we're entering things into our calculators or on computers. Now some calculators will actually have a cube root button or an xth root or 5th root or something like that. But most calculators, it's more efficient and faster just to enter things in using exponent notation. So for example, if I have the cube root of 100, I'm going to enter this as 100 to the 1/3 power. If you have an older model calculator, make sure that you put parentheses around the exponent. If you have the newer model calculators that take you up into a little exponent box, make sure you do the 1 divided by 3 there. Now the cube root of 100 is not a nice number. I can't think of a number that when I cube it, I get 100. But before we actually enter this in, let's think a little bit about what we know. We know that if I do 4 cubed, I get 64. And if I do 5 cubed, I get 125. So really what we're trying to figure out is what would I need to cube in order to get 100. So my answer should be somewhere between 4 and 5. And in fact, when I put this into my calculator, 100 to the 1/3 power is approximately 4.64. And we can always check by taking that number, 4.64, and cubing it. When I cube this, I don't get exactly 100. I get 99.897344. But remember, I rounded here when I wrote my cube root. So when I go and cube that rounded answer, it's not going to be perfect, but that is pretty close to 100. Okay, our next example is the 5th root of 625. And I'm going to write that in rational exponent form as 625 to the 1/5 power. I am using parentheses as necessary in my calculator model, and I get about 3.624 on my calculator. And if I'm checking whether that makes sense, I'm going to go ahead and raise that to the 5th power. And when I do that this time, I end up with 625.09 approximately. When I wrote down this answer, I had rounded up, so it makes sense that the answer that I'm getting is slightly above the radicand of 625. So now we're going to talk about general rational exponents. General rational exponents refer to an a to the m over n. So whenever you have an a to the m over n, what we're going to do there is we are still going to turn the denominator into the index, and then whatever the numerator is, that becomes the exponent on the root, and you can put it either inside or outside of the root. This is mainly used when we're trying to evaluate things or when we're trying to graph in our calculator. So example 3 says evaluate the following without a calculator if they are real numbers. So I see on the inside I have a 64 squared, and I was told not to use a calculator, so I'm a little unhappy with that. But I realize that this general rule for rational exponents says I can put that square either on the inside or the outside. So I'm going to go ahead and move it to the outside. Now I'm finding the cube root of 64, which is a nice manageable number. It's 4, and then I'm squaring that, and I'm getting 16. Okay, our next example, 49 to the 3/2 power. Well, that means the square root of 49, so this is a square root. And again, like the last problem, I'd prefer to put the cube on the outside to maintain smaller numbers here on the inside. So square root of 49 is 7, and then 7 cubed is 343. This next example should be written into your notes as 16 to the 5/2 power. So again, I translate to radical form first. It's going to be a square root of 16, then raised to the 5th power. The square root of 16 is 4, and I need to do 4 to the 5th. Now this one's a little bit tricky because that's higher than I'm used to going. I know that 4 cubed is 64, so if I multiply that by 4, it's 256, so that's 4 to the 4th. And if I multiply that by 4 one more time, then I will have my answer. 1024 is 4 to the 5th. Okay, D isn't really one of the expressions we're looking at, but we do need to pay attention to order of operations. So this one says do -10 squared and then square root that. So that would be the square root of 100, which would be 10. So it does matter the order in which you do things. And you might think that sometimes something like this, a square root and a square, would just cancel each other out. But as we can see in this example, -10 was what I originally put into this function, but 10 is what I got out. So we're going to examine that relationship a little bit more in the next example. So the next example says to graph y equals the square root of x squared in Desmos. What does it simplify to? Now before we start, a lot of people think that if I take the square root of x squared, I'm just going to get x. And it turns out that that's not the case. So let's go ahead and see what it looks like in Desmos. So here's what this function looks like. So I've entered in y equals the square root of x squared, and I can see that I did not just get y equals x. In fact, I got something entirely different, a completely different parent function. So let's cross off this initial guess. And what we see is that y equals the square root of x squared actually equals the absolute value of x. So let's think about why this might be. Let's think about putting in different x values into the square root of x squared. So if I put in a value like 0, I would be doing the square root of 0 squared, which is the square root of 0, which is 0. So 0, 0. If I put in 1, I'm squaring 1. Square root of 1 is 1. So 1, 1. If I put in 2, first I would square the 2. The square root of 4 is 2. So far everything's kind of behaving like we would expect it to. But what if I put something in like -2? If I do the square root of -2 squared, first I would square and get 4, and then the square root of 4 would be 2. So when I put negative 2 into this function, I didn't get negative 2 back out, I got 2 out. In other words, when I put a negative in, I got a positive out instead. So that's why this turns into the absolute value function. So the thing that we really need to remember here is when simplifying even roots, of variables, we need to use absolute values. So as an example, if I did the square root of x to the 6th, it might make sense to just say that's x cubed, but what we have to remember is that x could have been positive or negative, and this principal square root always outputs a positive or 0, so this is always non-negative. And if x itself were negative, when I cube it, it would also be negative. So the way that I fix that to try to keep this answer to not be negative is I put it in absolute values. So you're doing what you would think that you should do, figure out what multiplied by itself gives you x to the 6th, which is x cubed, but you're adding this additional absolute value to keep the answer always positive. Now luckily we don't have to worry about this with cube roots, so let's go ahead and look at what happens when we take a cube root, or for that matter any odd root. So in this next example we're asked to look at kind of the same thing, the cube root of x cubed, and actually what I meant to do on this, which it'll be fixed when you look at your notes, is the cube root of x cubed, not the cube of the cube root. So for this particular example, when I graph the cube root of x cubed, I do just get y equals x. And I can tell that this is y equals x because it goes through the point 5, 5 and 0, 0, so it goes through the origin with a slope of 5. Let's just make sure that we understand how this works. So let's say I put negative 2 in. I would be doing the cube root of negative 2 cubed, which would be the cube root of negative 8. And I'm thinking of a number that when cubed gives me negative 8, which is negative 2. So negative 2 is on there. Similarly, if I put something like 3 in, I'd be doing the cube root of 3 cubed, cube root of 27, which is just 3. So we'd have the point 3, 3 on there. Okay, so we're going to go ahead and stop there for video 1. We're at about 12 to 13 minutes here. And in the next video, we will talk about how to simplify when you have radical expressions.